Welcome to the first video of our unit on the periodic table. You've already learned a lot about the periodic table of elements in our study of atoms, but it's about to take on a whole new meaning for you. In this unit, we'll look at the patterns that give the table its signature look. But first, let's talk about the scientists responsible for creating what everybody recognizes as scientific, the periodic table of elements. Go ahead and pause the video and write down your essential questions. In 1869, scientists were grappling with the puzzle of classifying the elements. At the time, only 63 elements were known, and chemists could describe them with physical properties like boiling and melting point, or chemical properties like reactivity, but there really wasn't any sort of unifying order or arrangement of the elements. Dmitry Mendeleev was a Russian chemist who realized that the physical and chemical properties of elements were related to their atomic mass in a periodic way. In other words, when he lined up the known elements according to their atomic mass, certain patterns began to repeat themselves at regular intervals. Mendeleev arranged the elements by stacking rows or periods of elements each time that a pattern started to repeat itself. The result was groups of elements with similar physical and chemical properties falling into vertical columns on his table. His table didn't look much like the modern periodic table, as you can see, but it was actually very close to arranging elements in the order that we see them today. Sometimes this method of arranging elements meant that there were gaps in his horizontal rows, or periods. But the amazing thing is, instead of seeing this as a problem, Mendeleev thought it simply meant that the elements which belonged in the gaps had not yet been discovered. That's pretty bold. He was so confident that the patterns he had identified were correct that when elements didn't fit in, he claimed he was just missing some of the pieces to the puzzle. He was able to work out the atomic mass of the missing elements and predicted their chemical and physical properties. When they were discovered, Mendeleev turned out to be right. For example, he predicted the properties of an undiscovered element that should fit below aluminum in his table. When this element, gallium, was discovered in 1875, its properties were found to be scarily close to Mendeleev's predictions. Two other predicted elements were later discovered, lending even further credibility to Mendeleev's table. Mendeleev's table was 9/10 of the way there, but needed one important modification before it came the modern periodic table: the use of the atomic number as the organizing principle for the periods. Mendeleev ordered his elements in order of their atomic mass, and this gave him some problems. For example, iodine has a lower atomic mass than tellurium, so it should come before tellurium in Mendeleev's table. But in order to get iodine in the same group as the other elements with similar properties, such as fluorine, chlorine, and bromine, he had to put it after tellurium, so breaking his own rules. The same is true for cobalt and nickel. Using atomic number instead of atomic mass as the organizing principle was first proposed by this guy, British chemist Henry Moseley, in 1913, and it solved these anomalies. Iodine has a higher atomic number than tellurium, so even though he didn't know why, Mendeleev was right to place it after tellurium on the periodic table. When it was arranged by atomic number, and with the rapid discovery of many new elements, the periodic table began to take the familiar shape of the table that we use today. In the first half of this unit, we'll be considering the arrangement of the periodic table in terms of the chemical properties of the elements, properties like reactivity. The periodic table has more to it than just the learning objectives we'll cover. To really understand it, you'll have to study the quantum model of the atom in high school chemistry. In fact, with our understanding of reactivity and the use of the octet rule, we'll only be concerned with about half of the elements on the table. See these top numbers, these ones at the top of the table? They're called group numbers. Notice how there are two different sets of group numbers. One set is just numbers, and they represent the 18 groups or vertical columns of the elements on the periodic table. Below these, there's a second set of group numbers. They have a number and a letter next to them. 1A, 2A, and where the table dips, it changes to 3B, 4B, and so forth, all the way to zinc, where the table goes back up. Then the numbers go back to A's, starting with 3A and then 4A until we get to 8A. These are the group numbers we will be using most in this class, and they represent elements called main group elements. All these elements, the ones under the digits with an A outlined in red, are main group elements. They are the ones we're concerned with. The ones under a group number with a B, the ones in this dip, are called transition metals. I'll outline them in blue. The rules that we're about to learn don't apply to transition metals. So if you find me reminding you to skip the dip, this is what I'm talking about. Skip the group numbers that have a B. The group numbers that have an A, that's our focus. All right, to sum things up. Thanks to Mendeleev and Moseley, the periodic table we use is arranged in order of increasing atomic number and atomic mass. That's probably not new to you. As you move from left to right, or as you move down the horizontal rows, the atomic numbers and masses of the elements get bigger. In other words, the atoms of each element have more and more particles in their nucleus. Also, we are mostly concerned with the main group elements in this class. Main group elements are those elements in the columns with a group number and an A. Transition metals are in the dip, and we need to remember to skip the dip in this class. Thanks for watching.